Hi everyone, I am Foivos and I'm a second-year PhD student at the University of Edinburgh. My research interest is machine learning for compiler optimization and testing. Today I'm going to show you our approach for creating program embeddings using execution traces and how these can be used to develop a machine learning test oracle. So first of all, what is a test oracle? A test oracle is any mechanism that can judge program correctness based on the expected behavior. The test oracle is one of the four main tasks in the software testing field, and the other three are test generation, test execution, and test adequacy. All three of them, we could say that they are automated with tools like JUnit for executing tests, automatic test generation, and automated coverage tools for test generation and test adequacy, respectively. The test oracle still remains a largely manual process, and that means that developers have to spend time and effort to calculate the expected behavior of a program in order for them to develop test suites. Now, this is how a test oracle would look like in a real setting. Consider this simple test function with a set of test inputs here. These test inputs go into this function under test, and we can consider that as a black box, and we get an actual output. Now, we have to calculate what is the expected value for that specific function call and check if the expected value matches the actual one. These two lines here consist the process of the test oracle. So as you can see in this example, if the developers don't have an automatic way to get information about the behavior of a program given a set of inputs, that means that they have to calculate the expected outputs on themselves. So this is a very time-consuming process and it takes a lot of effort. So this is exactly why it is very important for us to automate the test oracle with some new method. So this is also referred as the test oracle problem, which is the challenge of automatically determining the correctness of test executions. And it is an open problem in software testing as of today. So in research literature, we can see mainly four types of test oracles. The first one is the specified oracle, which judges program behavior based on formal specifications. We have the implicit oracle that detects anomalies in executions like buffer overflows and segmentation faults. We have the derived oracle, which gets information from documentation, doc strings, and comments of source code. And more recently, we have the machine learning oracle. The problem with current machine learning oracle implementation is that they're either only used on inputs and outputs of systems under test without taking into account the internal state of functions at all, or they are evaluated on a tiny scale with some sample example programs or programming languages that are not used anymore in the industry. So on this work, we use supervised learning to classify execution traces of programs as passing or failing. In other words, we develop a supervised test oracle. We feel using execution traces helps the classifier learn important features about the internal states of a program under test. Our approach can be divided in three main steps. First of all, we develop an automated framework that instruments programs and collects execution traces. Second, we develop a method to represent execution traces as fixed length vector representations, which is one of our main contributions. Finally, we train a neural network to classify unseen executions within the same program as pass or fail. The first thing I'm going to discuss is how we instrument source code, how we collect all the execution traces, and then how we create labels for them before feeding them to the machine learning model. Well, first of all, we use the LLVM framework to instrument the code bases that we use. That means that our approach is language agnostic because any kind of programming language that can be compiled to LLVM with a compatible frontend means that it can be used in our approach. Our execution traces are basically a sequence of all the function invocations that happened during execution. In other words, we capture all the function calls that happen during the execution of a test, and we present the sequence of these function calls in a post-order way. That means that the function calls are stored only after the callee function returns back to the calling point. So each function call has three different types of information. separated in three sections. First of all, we get a pair of function names, one for the caller and one for the callee function. Second, we get the return values, and finally we get also the argument values. It is important to note that we're able to instrument all primitive, all composite, and all user-defined types like structs and classes. Pointers can be instrumented as well, arrays, and any kind of library or custom type. So let's consider this simple example on the left. Let's say that we have a set of test inputs here in the main function, one of them being a custom defined struct, and the second one being just an integer ID. So the function under test in this case is the foo function, and we're instrumenting the whole module. So foo gets as an argument the ID and the input struct, and then returns the ID plus bar of A. So bar just returns the X field of struct st, and then we return back to the main function and the status code is returned. So in this dummy example, this is how our execution trace would look like. So first of all, main would call foo, and then foo would call bar. So bar would return A of X, which means that this would be the first function call that we would capture in the execution trace. So in this function call, the argument is the struct, and the struct and the classes and all the other composite types are represented as a flattened sequence of all the numerical values that consist that data type. So in this case, the struct is represented as its fields, which is 20, 30, and 50. And the return value is A of X, which is 20. So after foo returns, we are going to capture the main to foo function call, and the arguments are going to be respectively 2, 20, 30, and 50, and the return value is going to be 22. And then we're also capturing the return statement of the main function in order for us to know when the program is terminating and how. And the return value in this case is 22. The second important part after collecting all the traces is how do we label all the executions as passing or failing. We start from existing test inputs from the code bases that we evaluate, and these test inputs can be human generated or automatically generated, and our goal is to train a neural network in as few traces as possible, let's say label 10 or 20% of the traces as pass or fail, and train on them and save the classification effort from the human expert to the trained neural network for the remaining 80 or 90% of the traces. So here we can identify two different categories for the source code that we use. It could be that a code base could contain failing tests that are based on real faults. That is very helpful for us because it means that we have both passing and failing tests, and that means that we just instrument the code base and we generate traces through the instrumented program. But as we all know, in most source code bases, there are only passing tests. And just because we use supervised learning, we have to give the model representations of both classes. And that is why we use an independent framework that does code mutations automatically. The mutations happen like this. We do one mutation at a time, and this mutation could be a swap in a binary operator or an arithmetic operator or a relational operator, and we check if this mutation affects tests from the test suite. So if we get failing executions, if we get failing tests by this specific mutation, then we keep that mutation and we run all the tests on this mutated code, and we generate a data set of both passing and failing traces. Balance doesn't matter. We have both balanced data sets of passing and failing executions, and we also have imbalanced data sets, very imbalanced in data sets, and we have seen that the model can still handle them effectively. Having discussed how we instrument the code bases and how we collect the execution traces and label them, let's see how one execution trace is fed into the machine learning architecture. On the bottom left, you can see on the gray box how an execution trace looks like. It is a sequence of function calls, let's say L0, L1, and LK. And this execution trace goes through two stages of encoding, encoder 1 and encoder 2. Encoder 1 summarizes one single function call, and then each function call summarization goes to encoder 2 that summarizes the whole trace. Finally, the output goes into a feed-forward network of 3 layers that does binary classification. So first of all, we have to somehow create a function call representation as a fixed length vector. So as I said before, one function call contains 3 different sections. This is 2 function names, the return values, and the arguments. So first of all, the return values and the arguments that are numerical values are represented in 64-bit binary arrays. As far as the function names are concerned that are strings, we one-hot encode them. We have 2 LSTM encoders that have an input size of 64 and take each one of the numerical values at each time step and encode them. So finally, we end up with a fixed vector representation called TI that consists of 4 different sections that have a fixed size and they are concatenated. This fixed vector TI represents one function call and contains the encoded arguments, the encoded return values, and the function names. Now that we have summarized each function call as a fixed vector, we can pass all these representations as a sequence to the second encoder and summarize all of them into a fixed vector representation of the whole trace. Now, this representation of the whole trace is passed into as an input to the feed forward NN, and of course the learning objective is the binary classification of the trace as passing or failing. For our evaluation, our main objective is to effectively identify all the failing executions in a given program. So this is why we use the failing executions. We represent the failing executions as the positive class. We do measure precision, recall, and specificity with respect to the percentage of traces used for training. Finally, we use our test oracle to compare it against a hierarchical clustering test oracle approach that had been introduced back in 2017. And even though it is an unsupervised learning technique, which is different than the supervised learning we use, we feel it is relevant to compare against it because it is the current state of the art in test oracles. So for our evaluation, we use 5 different case studies from 4 different large-scale, complicated and well-maintained code bases like Ethereum cryptocurrency, PyTorch, Microsoft Seal encryption library, and the Linux stream editor SED. So out of all these 5 case studies, we were only able to get real faults, real failing tests for SED because they were available in SIR repository that contained previous versions of the source code that had real bugs identified later. So for the remaining 4 modules that we evaluated, we had to do the random mutations that I explained before, and essentially we seeded faults, leading to balanced data sets between passing and failing tests, up to way imbalanced data sets. But it seems like our model was able to handle all of them appropriately. In this slide, you can see the 3 most representative plots from these 5 case studies, and you can see the precision and recall with respect to the percentage of traces used in training. As you can see in Ethereum and PyTorch, just 10% of the total traces for training means that we are able to get a well-performing classifier on the rest of the unseen 90% of the traces. For seal encryptor, we need more than that, which is explained by the fact that seal encryptor had a very imbalanced data set of passing and failing tests, and a larger percentage was needed to reach eventually a good performance. One thing we might notice is that for Ethereum, if we use too many traces for training, this could lead in some kind of overfit, shown by the decline of recall when we use 30% of the traces. Now let's take a look at the full table of the results of our implementation and how do they compare to the hierarchical clustering approach. First of all, as you can see, we use on average just 15% of the total traces for training, which on a real setting means that the developer would have to just manually label as pass or fail 15% of the total traces and classify the remaining 85% effectively using our model. As far as the precision, recall, and specificity are concerned, we notice that our model is able to perform well in both balanced datasets like Ethereum CD and imbalanced datasets like SED or PyTorch. In some cases, like the seal encryptor or the two modules from Ethereum, our model is not able to get more than 90% in precision and recall. And that is maybe because these specific modules were quite huge. There were millions of lines of code that resulted to very large execution traces, and so maybe the information was a bit too much for our model to achieve a greater performance. So as far as the hierarchical clustering approach is concerned, I would notice that in the two last case studies, seal encryptor and SED, it is not able to classify any of the passing or failing executions. And in the case of PyTorch and Ethereum, it either achieves a maximum precision or a maximum recall. So in the case of maximum precision, that means that the model just generalizes everything as a failing execution, and that results to correctly classifying all failing executions as failing ones, but also classifying all passing executions as failing ones. And exactly the opposite for the maximum recall. So we believe that our approach is better in the sense that the model is able to handle both failing and passing classes accurately and distinguish between them. There is only one example in the table, one case study that we do worse than the hierarchical clustering approach, and this is the common difficulty module from Ethereum. So we get a precision of 80%, recall of 82%, and true negative rate of 79%, whereas they get maximum precision and true negative rate and 0.49 recall. Now I'm going to conclude with an ablation study that we did on the model to help us understand which section of the trace is more important. Maybe if some section was redundant and we didn't need it. So we snipped out from the trace one section at a time, and we retrained the model in the exact same setting. And we got the following results. Now, as you can see, removing the arguments had a detrimental effect on the performance of the model in all 5 case studies. So that means to us that the arguments were really important in the execution traces as pieces of information for representing the executions. As for the return values, you can see that in 3 out of 5 case studies, the performance dramatically drops. But in PyTorch and Ethereum Seal Engine, they are not hugely affected. Finally, as you can see, removing the function names also leads to a significant drop in the performance of the model. So this eventually leads us to the conclusion that all 3 sections are equally important and we shouldn't omit any of them. So this is all. Thank you very much for your attendance.